All right, where were we? So, at the beginning and the end, this object has no energy. So what happened? Well, clearly, my person at FG, FN, those are balanced. I have F person and F friction. So what happened was the person did positive work to my system to get it to move, and the friction did negative work to my system to take energy out. So the net change in energy in the system is 0. Even though it moved, the person added energy into the system so that it could move. If I drew a middle energy bar chart, it would have been moving, probably at constant velocity, right? But when I push it and it ends, the person added work to the system, friction took work out of the system, and so I end up with an energy bar chart at the end with still 0 energy, all right? Before we go too much further, let's make sure we understand some things about when work happens and when it doesn't, and its direction. So the only way for work to happen is if the distance covered is in the same direction as the force. So I'm holding this book. Currently, I'm doing no work to the book because the book is not traveling a distance. So right now, I'm not doing work to the book. If I raise the book up over my head, I've done work to the system because the force I applied, the normal force, up, is in the same direction as the distance the book went. So the book went up and the force was up, so I would have positive force, positive direction. I did positive work to the book. Now, if I move the book from over here to over here, I have done no work to the book because the force I'm applying to the book is the normal force, pointing up. And the distance it just moved was horizontal. So I did no work to the book because the force was perpendicular to the direction traveled. So the only way work can be done, work only occurs if the force is in the same direction or is parallel to, we'll write parallel to, the distance traveled. So, if you carry a heavy weight around, this is a heavy dumbbell. You carry it around, you take it over here, you take it back over here, you take it over there again, all the ways. You have done no work to this barbell at all because you did not apply a force parallel to the direction traveled. The direction traveled was horizontal, but the force you're applying to this barbell is upwards. Those are perpendicular to each other. So none of that force counts. Now, if you lift the barbell above your head, now the force is in the right direction. Okay, so what happens if I apply an angled force? So what if I have a box and a string, and like we did in Unit 2, I pull the box at an angle above the horizontal? Well, when I draw the free body diagram for this force of pull, or this force of tension, there would be a component Ft sine theta going up, and a component Ft cosine theta going to the left. Only Ft cosine theta can do work because you're going to pull the box horizontally that way. So only the component of the force that's parallel to the distance can do work. Okay? So another way that they write this equation is with a cosine theta next to it. This theta being the angle between distance and force. If the force isn't directly in line with the distance, it's at some other angle, then I have to not just use work is equal to force times distance, I have to use this FD cosine theta, because only the part of the force that's pointing in the direction of travel, the direction I'm moving, only that force can do work, right? Last thing, the work energy theorem says that if I make a system of just the object, remember, if the system is just the object, so maybe you have a system that's not just an object, but at the very basic level, an object by itself is a system, right? This is a system, I'm a system. If I don't include anything else, an object by itself can be a system. What's the only type of energy that object by itself can have? Kinetic. So if somebody does work to an object that's a system all by itself, that work has to turn into a change in kinetic energy. So this is the work energy theorem. And it says the work has to turn into a change in kinetic energy. That's a very basic way of looking at things. If we include other types of, or if we include earth or a spring in our system, it's possible that work is taking away kinetic energy, or it might be taking away gravitational potential, or it could be taking away spring. So this is only a work energy theorem in the sense that if the system is only an object, not earth and not a spring, the only type of energy it could have is kinetic. So work must turn into a change in kinetic energy. Either I add work to the system and my kinetic energy increases, or I subtract, do negative work to the system, take energy out, and reduce the kinetic energy. All right? If you're like, but what if I got rid of all the kinetic energy? Could it be negative? Like, what if I kept doing work to the object and I ran out of kinetic energy? I had like 10 joules and then I made 0 joules. Would I still be doing work to it and I could make negative joules? Can kinetic energy be negative? It can't. And the way this doesn't happen is because of the distance. If you do so much negative work that all the kinetic energy is gone, then what's the speed of the object? 0. So is the object going to travel a distance? No. So there is a limiting factor. You can't do work to a system to make negative kinetic energy, because once it runs out of kinetic energy, it's going to stop moving. And unless you add energy into the system, this book isn't going to get negative kinetic energy. All right? All right, thanks. Sorry it's split into 2.